that and fiddling around with it, you won't accidentally bump your hand or a tool or something into the surface of this mirror. You want to have a little gap just for safety. And also, let's see, what else was I going to say? You'll have to have, of course, the tube extension, because this is going to stick out a lot way farther. The Newtonian diagonal would be right here. So this is going to make the tube a lot longer. Another thing that you have to think about is that what happens is with a Gregorian or a Cassegrainian telescope, what happens is if you look here, you'll see that there's a little bit of surface of the diagonal that's outside this cone of light from a star. And what happens is light from the background sky, light rays can come along here, intersect this, and go right up to your point C. And that means that light from the background sky that you don't want to be here is actually fogging up your image a little bit right there. Now that's not too serious of a problem with a bright object like the moon or a bright planet like Mars, because they have lots of surface brightness. And you could still get a pretty good view of the moon or Mars or Saturn or Jupiter or something like that without doing extra baffling. But what you want to do, if you want to look at deep sky objects like star clusters and galaxies and nebulae, is you have to figure out some way of preventing this light from the background sky from ending up at point C. So what you have to do, and I did that with my own Gregorian telescope, and I think I showed videos of that when I was putting them on YouTube, is you have to make two light baffles, similar to a Cassegrainian. You see this dot right here that I drew? And that dot right there that I drew is just, so I wouldn't make the diagram look too complicated. That is the front end of a baffle tube. It's just a hollow tube like a mailing tube or a sonotube, something like that, a cardboard mailing tube you can get from Staples or some stationery store like that. And the tube actually runs from about approximately the same diameter as the secondary mirror, maybe a bit larger. And it'll come down with an open end here, and the open end will be about here, and then another tube runs from here up to here with an open end right up to this point, and on either side, like it cuts across here, there's the open end of the tube right like this. So there's two basic tubes, and what happens is a light ray coming along here can't get over this way farther than the open end of this tube, and so it'll go by here, and then it'll end up on the other side of C, outside your imaging area where you want to look. And if you want to figure out how to do that really rigorously, there's a book called Telescope Optics, Evaluation and Design by, let's see, Rutten and Martin van der Rohe. I think it's available from Wilman Bell, just like Sky and Telescope is. And they give detailed ways of describing how to do really good light baffling. One objection that I have with their light baffling techniques is, well, I'll put it this way. What I like to do with my light baffles, inside the tube, put a lot of narrow ring baffles along without like going too far into the tube. And that will give a little bit of airspace around the optical path. And the same thing with the main telescope tube. You could have baffles like ring baffles just protruding out a little bit, like just narrow rings. And with sharp edges, like pieces of cardboard cut into a ring form, like that black cardboard you can get at a dollar store or at Walmart. And then line the whole tube with those, and that'll keep stray reflections from reflecting off the inside of the tube. And the same with this little baffle tube here. It's not that easy to do. It takes a lot of work. But eventually, if you want to cut out all stray light, or most of it, from entering this area right here, you have to have really good baffling in there. It's quite a job. Anyway, maybe I'll do a video of how I made the baffle sometime for my 20-inch Gregorian. It took quite a bit of work to do that. But anyway, this is a very complicated arrangement, but compared to Newtonian, but it can be very effective in certain circumstances. One really good advantage this would have is if a person, say, had a really large telescope, say a 20-inch f5 or a 30-inch f5 Newtonian reflector, and they didn't want to continually climb a tall ladder to look through the Newtonian eyepiece when it was aimed like high in the sky, nearly overhead. So this will fold the light down back to near the bottom of the telescope tube, And when the telescope is aimed overhead in the sky, you could be sitting in a comfortable chair right on the ground, right near the ground, looking through the eyepiece without having to climb a ladder. And that's one of the big advantages that my Gregorian telescope has, is you can do that. And the top of the tube is way high above the ground, like really high up above the ground. But the eyepiece, for most spots that I observe in the sky the way I do it, the eyepiece right here is close to 4 feet off the ground. And I can stand and look through it comfortably, or I could sit on a tall chair and look through it. It's a very comfortable way of looking, and you're not distressed at having to balance on a tall ladder and wondering if you're going to fall off onto a concrete floor if you suddenly just sort of momentarily have a lapse in your thinking, you lose track of where you are. It can be kind of dangerous to look through a tall Newtonian telescope. So that's one advantage that this has, and you can get by with a very inexpensive secondary mirror that you can just get in an ordinary small, cheap, inexpensive Newtonian telescope. And the main thing is, though, that this has to have a fairly smooth, accurate shape, and so does this primary mirror. But I think the difference between the ellipsoid and the paraboloid and that is not going to be very big in terms of actual wavelength. But anyway, it's pretty. What a person could do, like this gentleman that asked me the questions about the Gregorian, if he finds that this is too much for him to build, then he could leave his 13-inch Dobsonian just the way it is and enjoy using it with low and high power eyepieces, and then he could use his 4-inch f4 as a portable telescope that's very easy to lightweight to carry around. You could carry it out in a few seconds and have a quick look around the sky, and then bring it back into the house when you don't feel like, for some reason, like setting up a large heavy 13-inch telescope. So there's an advantage to having a small portable telescope and a very large one as well. So his money buying the 4-inch will not be wasted at all. It wasn't very expensive, and that's a good way to get around having to build the Gregorian. But on the other hand, the Gregorian could turn out to be a really good thing. So one thing about it is the long focal length eyepieces here that give high power with the Gregorian, they will give better eye relief and also have better image quality near the edge of the field of view than a short focal length or eyepiece at the Newtonian focus. However, there are eyepieces made now with long eye relief and very short focal lengths that can be used in a Newtonian and give very high power. And you could also, like I mentioned, buy a good Barlow lens and put it in there from a really good, reputable manufacturer of eyepieces. So anyway, there's all kinds of... Also, I would advise... I'm almost out of time now, so I'll advise more information can be obtained by doing a Google search on Gregorian telescopes. By the way, the Gregorian, just do a Google search and read what the internet has to say about it on different websites. And they give a design drawing similar to mine. And then also, I should mention that this Gregorian was actually named by a 17th century mathematician named James Gregory. And he was the one that invented this design in the first place. So this is a very old design. In fact, this is the oldest design for a reflecting telescope in existence. The Newtonian actually came a bit later than that, and it was invented by Isaac Newton, but I think the Gregorian was first. So anyway, it's a very elegant design, and I hope I haven't left anything out the person would need to know. But anything I haven't said was probably in either telescope optics, evaluation and design, or How to Make a Telescope by John Textro. Well, goodbye. I think my time is almost out. Goodbye. Actually, I'm deciding to, I think I'm going to record just a little bit more, since I'll be using 2 videos anyway, and probably less than 15 minutes each, because that's the YouTube limit in time. And I thought I'd mention a little bit more about how to mount these 2 mirrors. Okay, actually the 3 mirrors. Textro, I think what the gentleman that asked me the questions could do to try, maybe, since he has to have a baffle tube anyway, he could maybe, since the mirror comes in its own mirror cell as a Newtonian, As long as the mirror is not likely to fall out of the Newtonian when turned upside down, he could leave this secondary mirror, the 4-inch, in the Newtonian tube that it came with, and remove the spider that holds the Newtonian diagonal and the eyepiece holder, and just use that as a combination of a device to hold that in place and a baffle tube. And then this could be mounted on its own separate spider, just like an ordinary Newtonian diagonal would, only reversed. Like in a Newtonian, the reflecting surface of the small flat mirror faces toward the primary mirror, and in this case, it faces away from the primary mirror, as you can see from the diagram. And eventually, like there's special ways of mounting this. You want to make sure that this is absolutely securely in place, so that when the telescope is pointed up toward the sky, that the edges of this mirror will be supported by, say, 3 or 4 little clips that are quite strong and won't let the mirror accidentally fall out of it. So this mirror is going to be upside down compared to what a normal Newtonian mirror would be. And also, the best material to use for these baffles and for the outside of the telescope is either wood or cardboard, because it has a very, like a low transmission rate of heat, and it's thermally stable. It doesn't conduct heat very well, and according to Texro, it will not cause as likely to cause tube currents that will distort your image. So there's a lot to think about with telescopes. The same with the outside tube. Wood or cardboard for a small telescope like a 13-inch is really pretty good. I would avoid using a metal tube here for the baffles at all if you could. And let's see, there's a special type of flotation cell that might be a good idea to have for that. For a 13-inch mirror, a 9-point flotation cell is good. I used for my 20-inch an 18-point flotation cell with 6 triangles. They're almost equilateral in shape, and at the center of each triangle of wood is a little hole that I drilled through it with a little metal plate in the top, and that balances like a child's teeter-totter on the tip of a bolt, a collimating bolt that's in the back of the primary mirror cell. And then each of those wooden triangles actually balances on a bar that balances on a bolt. Actually a pair of bolts, so that the bar won't slip sideways like this way. And so it's an 18-point flotation cell, and there's like you can, for various sources, you can get the actual dimensions that you need for the triangles. I think the 13-inch Coulter telescope that this gentleman bought, pardon me, it actually comes with its own flotation cell, which is a 9-point cell. It's pretty good. Okay, but this one, I don't think you really need a flotation cell for the small 4-inch mirror. Just need some clips and that'll balance, like hold it up around the side and on the outside. And it's also got to have some like bolts that'll, with springs or some kind of a mechanism that'll allow you to tilt the mirror like either sideways like this or up and down like this. It's got to be 3-dimensionally tiltable to get it actually aligned with the whole optical system in 3 dimensions. Okay, actually when you look through this eyepiece focuser without an eyepiece in there against a bright sky, what you will actually see is a series of rings. And the first ring will be the outside of this mirror, with no baffles in place. Say the first ring will be the outside of this mirror, and then the next ring will be the outside of this mirror right here, and the third ring will be the outside edges of this mirror. And if you get all 3 of these rings concentrically aligned up by the various tilting methods, then your optical system will be very accurately aligned. Like Texrel describes how to do that. It was actually fairly easy to do with my 20-inch Gregorian. The hard part I found, the really difficult part with my 20-inch Gregorian, was shifting this mirror back and forth here to get the focal point C in the right spot to where my eyepieces would actually reach it with the size of the focuser I had. So that's quite difficult to do, and as I say, you're going to have to be able to move this back and forth in very small amounts, and also, if necessary, to move this back and forth quite a bit. Because I say, I'm not just sure what the exact distance between point A and B is. And like I say, I could figure it out with a quadratic equation.